Okay, so we start with discussion on those directives that we had been including. I mean that slash include directive in our program. So these are what we call as all the directives that are indicated by hash mark, like this include. So hash mark include. So these are called preprocessor directive, and C preprocessor does lots of things before the program is handed out to compiler. Preprocessor is not a compiler, but the compiler, when you invoke the compiler will first feed the file to C preprocessor. Preprocessor will read all the directives that are there for the preprocessor to process, and those are indicated by this hash mark. And there are certain operations that are done accordingly, and then the source code that comes out of the preprocessor, that is then compiled to transform the higher level language code into machine language code, and to generate what we call as object files. And then those object files are linked along with system libraries that may be required, and after linking with system libraries, whatever the user uh, libraries are there required for the execution, then you get to executable file, which is then used to run the application. So that in essence is the complete process of compilation. Now preprocessor, in addition to these directives, also does lots of things. For example, it strips the code of all comments. So that is another reason why you should never be stingy while using comments. Be liberal and be uh, amenable to err towards the size of being verbose. Right? Write too many comments, as many comments as you want to make the program or logic of the code understandable. All these comment lines would be stripped off by the preprocessor. So your executable or the program code is not really what gets affected by your comment lines. So feel free to include as many comment lines as required, uh, whatever improves the readability and understandability of the logic of the code. Then the most commonly used preprocessor directive include does just that. It includes the relevant file at the location where it is asked. So include iostream would look for iostream.h header file and copy the contents of that file and paste it at the location where that include statement occurs. So the complete code that is passed on to the compiler, that would include the copy of iostream header file at that location. Similarly, we can use symbolic constants. For example, instead of having these magic numbers scattered all through the code, just as an example, we write here 3.14159. That's the value of pi. So instead of writing 3.14159, the code is much more readable if I write it as pi. So the syntax or the meaning is obviously very clear. So what does this do is whenever you use pi in the code, preprocessor will replace all instances of pi with this value, right? So your code might be written in terms of pi, but preprocessor will replace all instances of pi with this numeric value, and then it is sent to the compilation. And therefore it is a very convenient way to define the size of array or some object size or some memory storage amount of memory that you need to use or storage that you need to use, and that can be scaled by just one change in this defined parameter, and your program can scale automatically from addressing or containing with requiring working with very small amount of storage to a very large amount of storage. Problem size can be changed very easily. So this define statement define hash define pi 3.14159. This defines a symbolic constant pi and which remains defined until the end of file, or this defined is nullified by an undef statement. So every defined statement can be countered by an undef hash undef command. Undef pi would nullify this association of pi with this constant, and from that point onwards pi is again just another identifier. Undefined shortened format. First we define pi, which is mapped to a constant 3.14159. Right? So as long as this remains in force, pi, every instance of pi will be interpreted as equal to 3.14159. But once I declare that, or once I break this association by using undef pi, then that association from that point onwards is no longer there. Pi is a free variable, right? It may even be not defined subsequently. It may also trigger an error that pi is undefined or undeclared variable identifier, right? Before the advent of inline functions is a more recent addition to the programming language, where inline qualifier allows the function to be included as a statement in the code, right? So that is much faster because function calls would require additional overheads in the data transfer, control passing to the function, and then control returning back to the calling main driver function, right? So an inline function would expand the function in place, avoiding these overheads of control transfer and also data transfer. So that is possible in case of small functions. But before this inline feature was there in the programming languages, macros were defined, used during preprocessor directive of define, and small operations could have been or were easily managed by defining these macros. For example, a simple function in this example computing the extracting the maximum of two arguments, whichever I mean given the two arguments x and y, return whatever is the maximum. So by using ternary operator, so we define this max and with two arguments, and this will be replaced by this ternary operator, right? So ternary operator essentially just checks for the condition if x is greater than y, return x, else return y. So that is what is done, but it is much easier to understand, much easier, much logic is much more clear. It is much more readable if I use this macro by the name of max. Similarly, you can define for min and max, similar other simpler uh, operations that do not require too much of complex arithmetic or complex compound statements. They can be defined in terms of macros and without causing any confusion. But with the inline functions being provided for in the recent versions of the program, uh, it is there since 99 version of the edition of C and C++ language standard. So with inline functionality being there, macros really do not have much use now. But just to be aware, you should know that there is something, uh, you can work with simpler expressions using define directive by mapping it to a macro expansion, macro calls. Then preprocessor can also be used for conditional compilation. For example, there are some very good functional libraries in C, or for that matter any other programming language. And if you are working with C++, then in order to use those C functions, you need to declare those to be external to this code, right? And those have to be declared as external C language code, right? So if you're using a compiler and you want to use you want to be automatically, if compiler if it is a C++ compiler, then the code needs to be declared as external C code. If it is a C compiler, then it would be compiling straight away, right? Sometimes single compiler does both the options. So version which mode it is being called, that determines. So when you invoke C++ version of the compiler, or when you invoke C++ compiler to compile certain code which contains C functions as well, then the there is a constant which calls like C++, 2 underscore followed by C++. So this symbolic constant becomes defined when you use a C++ compiler. So then you can test for this condition whether if this constant C++ is defined, and that is by using the keyword if def. If def stands for, hash if def, so it would be if def C++, right? Or if I'm testing, I can as well test this as if not defined. If ndef is if not defined C++, then you can first define C++ and then use extern C and then define whatever code you need to use here, include whatever libraries you need to include for C language library, right? So and then this define can be then negated by C++. So this C++ becomes undefined from this point onwards of the code, right? And again the programming, the compilation happens as if C++ was not defined. So these are the conditions where you can use these combination various conditional compilation with whichever way it is possible. So define if def, if not defined, if and def, and then if, then you want to use, if you want to use else if, then that there is, this is in the preprocessor it is called L if, and then else clause, and finally end this if clause by end if, hash end if, right? Then error is a directive which is a very powerful directive to indicate, to communicate error. Something unexpected happens, you want to signal an error, then just using a preprocessor directive of error, the output of that would be directed to standard error. So standard output is C out, standard error is C error, right? So C error, CERR, right? So C, so this will send the message, error message, to standard error. The difference between standard output in the case of computer video display unit, both of these are mapped to the display unit, right? Standard output will also standard error. Standard error is also one output stream. The only thing is it is only reserved for the flashing the error signals, and it does not wait for whatever is in the pipeline. It will just flush out whatever contents need to be displayed. It does not wait for anything else. No, that error is different. I mean, these errors need to be tracked. I mean, there is something unexpected happens. That's how you write uh, literate programs. The program should be able to send you helpful or give the user helpful messages if something goes wrong, right? So those errors need to be trapped, and then those need to be communicated. So those error messages are generally directed towards standard error. So standard error will not wait for any uh, flushing of the output buffer. The contents would be just displayed straight away. Right? So it is quite possible that standard error will overwrite whatever is being currently scrolling through the screen. So error directive prints specified tokens and aborts preprocessing and compilation. So that hash error is only the error during the preprocessor processing. But you can also have uh, need to trap errors during the execution running of the application. So even those cases, some helpful messages, you need to trap those errors, and some helpful messages should be conveyed to the user, and those messages are sent to standard error. Right. So some of the examples of the sizes. So if table size is greater than 200, then you can undefine the table size, whatever is previously mapped, and then again define, right? So 200 or some other value. So just before you define it to some other value, it needs to be first delinked from previous association. That's what this trivial three lines of code actually trying to convey, right? So table size has some value associated with it earlier. So if that table size value is greater than 200 and you want it to be limited to 200, then you can just undefine this table size association with whatever value it was pointing to earlier, and define it to mean 200 from this point of the code onwards, right? Else if, that's another lower end of the bracket spectrum, if the table size is defined as some value less than 40, again you need to delink that association, and then let's say define table size to be equal to for 50, not 40, 50, right? Else you can have undefined, whatever is the, if it is outside this range, then you can again delink this table size from whatever value it was meant to represent earlier, and you can define it to have value of 100 from this point onwards. And then this table size can be used to declare the array size. So table is declared to be an array of integer data type of size 100 in this case, right? So we'll come to the discussion of arrays. What is that? What do we mean by arrays? Arrays are the most primitive form of data structures which allow you a logical way to access large amount of data, right? By definition, an identifier can only point to one location, one data point, whichever type of data it is pointing to. But if I'm interested in accessing, if I'm interested in processing a large number of data of similar type, then I can define, I can do so by using arrays, right? So these arrays need to be defined what size of how many data points that I'm interested to work with. So that is what we call as the size of the array, right? So these array sizes need to be known at compilation time. It cannot be done. It is wrong. The program will not compile if I prompt the user for input. What is the array size that you want to declare? Take that integer as an input and then declare the array of requisite size. That is not possible. At least that is not possible in the standard way the arrays are defined. Right? The size of the array that needs to be declared needs to be known at the time of compilation, and therefore it is possible to do so by define directive of preprocessor, because that mapping of table size with a numeric figure will be accomplished before the code is sent for compilation. Preprocessor will operate and do all the replacement of table size with appropriate number, numeric value, before the code is actually sent out to compilation. Right? So that's an example of C++ symbolic constant being defined. If not defined C++, we flash an error. A C++ compiler is required if you are writing a C++ code, if you are trying to compile a C++ code, and if you are trying to compile it using C code, C compiler, it would flash this error. Right? So preprocessor is of course a much more versatile and much more powerful tool which can do a lot more things than what we have discussed in these two slides. I have shared a note by Professor Richard Stallman on GNU C plus C preprocessor on the classroom portal, so you can have a look at it. And also the first basic introduction to C++ in Frank Boken's CPP annotations. That also gives a very good discussion of conditional compilation using preprocessor macros. So both of these resources, I mean, Stallman's note is rather comprehensive and it is a very good read, very good resource for reference, but not all features that are described in Stallman's note are normally used for usual normal programming. But it is a very uh, it just allows you to see the functionalities of C preprocessor, what it can do. I mean, the whole idea is to not let you think that preprocessor only does include and define. There are lots of things that C preprocessor does, and more importantly, and more in the present context, the pragma directives. Pragma are practical instructions to the compiler. So there are many pragma directives which help in compilation of the code, and the simplest way to do parallel programming is using pragma directives with OpenMP. OpenMP pragma directives which allow you to uh, distribute the tasks between different processors on in your computer. Now, uh, all computers, even the portable computers these days, they come with processor with multiple cores, isn't it? How many cores does your computer have? 8 cores. So 8 core processor will be able to run at least 16 jobs in parallel. 16 threads. So that is what I'm saying. So every core will typically have 2 threads. So 2 threads, what are these threads? Threads is that line of instruction flow, right? So single code that we run is a single line of flow, instruction flow. So that is one thread. So 16 threads can accommodate if your processor has 8 cores. So it can run concurrently 16 processes. So how do you run concurrently 16 processes? I mean, your hardware has that facility, but unless you know how to use that functionality, you cannot use it. That is where your programming comes. So the simplest way to harness that multiprocessor capability is by using OpenMP uh, extensions, OpenMP uh, features in by using pragma directives. So what OpenMP does is uh, it calculates how many processors are there, how many threads can be run concurrently, and then divides the job, whatever you instruct where, I mean, that pragma needs to be defined by you, that this particular uh, loop repetition structure needs to be executed in parallel by using OpenMP. So that for loop or while loop, it will be split into parallel executions in as many threads as required, and after the end of that, results would be collated again, and then again the program resumes. Right? So that is the simplest way to harness multiprocessor capabilities of your computer, which are very common these days. Symmetric multiprocessor computers, all computers today, they come with multiprocessing capabilities, and that can be very easily harnessed by using pragma directives of OpenMP. Right? Pardon? Yeah, that is done automatically by OpenMP. Yes, everything is done by the processor. So when it hits the pragma directive, pragma line, then it will start calculating, okay, this for loop, for example, I define pragma directive for OpenMP is for loop, this index needs to be executed in parallel. So then it will decide how many times that loop has to go. So if it is 100 uh, iterations, 100 loops, then it will try to balance it maybe 12 in each core, right? Hmm. Clock frequency, that is instructions per cycle. Normally, uh, all cores, as I said, the threads will run independently. Every thread will run independently, right? And at the end, it will wait until all the executions have completed, and then results will be compiled again, and then you can go ahead with that point, right? So different cores operating, running at different clock speed really doesn't matter. It will only increase the latency time. Some core might have to wait for next amount of data to process before until the execution is completed at the other end of the core, at some other core. Those are graphic processors, GPU. GPU, they are similar, but they normally have very large number of cores because their numerical precision is not much. You don't need as much numerical precision for graphic rendering. So it can handle only single precision arithmetic. GPUs do not have double precision or extended precision. CPU is complete arithmetic. So it can do, it has full functionality of whatever, I mean, double precision arithmetic can be done. Extended precision can also be defined and that can also be done. GPU cannot handle that. And that is why it is because it cannot handle because it is not designed to handle that because you only need to calculate the pixels and how that pixels need to be modified and that can be done very easily. It does, it does, but that it does only using single precision arithmetic. It does not do double precision arithmetic. So that is why because it has to do only single precision arithmetic, its design and its manufacture is cheaper than normal processor. Capability is a very it is a very special purpose processor, right? And because it can handle single precision arithmetic and we use it for numerical calculations as well because it comes in large massive amount of cores because it is cheaper to produce because you don't have to account for double precision and extended precision arithmetic in that, right? So it is cheaper to produce. So computers would normally come with graphic card with graphic processor unit. So they would have massive parallel processing capabilities, and they can be used, right? But that will only be uh, limited precision. But for most of the engineering applications, single precision is generally adequate, right? So we'll stop at this point from our next lecture tomorrow. We start with the concept of structured programming, that is how we divide the problem solving into a set of tasks and then implement different tasks in different modules and then look at problem solving as combination of different modules. So this is what we call as modular approach to programming or structured programming. That was what was enunciated by Professor Edgar Dijkstra. So that's the topic for tomorrow's discussion. So stop here.